I'm Er-Cheng from HashCloak, and I'm going to talk about recursive proof composition today. And this is my agenda. I will first talk about the motivation of why we consider recursive proof composition. And after that, I will go to formulate a version of proof system called SNARKs. And after that, I will formulate a data structure called proof carrying data, PCD. And this PCD have some useful properties we would like to have. And next, I would give a high-level idea of how to construct PCDs with SNARKs and the technique of recursive proof composition. Okay, so let's start with the motivation. So let's think of the scenario of the blockchain. And the blockchain would start with the genesis state. And as the time goes by, there will be transaction, and there will be state transition from the genesis state to the first state, and it goes on with time. So the state transition will keep happening. And now if someone wants to join in this blockchain and to see if if the data, the state they get is correct, like for example, if they get state 3, and they will have to validate if state 3 is correct. And how do they do this in a naive way? So to verify state 3, this verifier have to gather information from the initial state and transaction batches 1, 2, and 3, and try to execute the state transition from the initial state and all along to state 3, and see if it matches the data of state 3 it have in hand. And as we will see, this process is not so scalable, because as time goes by, this history of state transition becomes very long, and the verifier have to gather information that will become longer and longer as time goes by. This is not very satisfiable. So let's consider a second option to do verification. And the second option is to let the verifier delegate its work to another prover. So now someone can come out as a prover, and the prover will gather all the information needed in the previous stage. So it gathers all the states and all the transactions along the history, and the prover can do a global computation and produce a proof. And this proof is short, and this proof is like the size of the proof does not grow with the size of the blockchain. So now the verifier can take this proof and verify it very quickly. So this is like very good to the verifier, because the verifier doesn't have to do a lot of information gathering and computations. But now the problem will be that the prover will have a very big load, because the prover still needs to gather all these information and do a lot of computation, and this amount of data and computation will grow in size as time goes by. So this is not a fully scalable version if we want to do the whole verification process. So the third option is to somehow let the prover also generate the proof more scalably, and this can be done by considering a data structure called proof carrying data. So in proof carrying data, we can consider letting every state accompany another proof, and the proof is going to validate the state. So let's consider now we are in state 2, and there's a proof 2 there. Like the proof is still going to be produced by the prover, but the difference between this option and the previous one is that generating the next proof, proof 3, does not require the prover to have all the previous states and transactions. Now the prover only needs the previous state and proof, so state 2 and proof 2, and also transaction batch 3. So the prover only needs these information to produce the current proof. And this is like reasonable, because in order to say that state 3 is valid, we only need to know there is some previous state which is valid. And the previous state transits to this current state in a valid way. So these information are all captured by the previous state, the previous proof, and the current state transition data. So now the prover only needs local data and local computation to produce a proof, and does not have to have the burden to collect all the history data. So we would like to construct such a data structure called proof carrying data. And we can see that in this proof carrying data structure, when the prover tries to generate a proof, the prover actually have to, like in its proof, it has to prove that the previous proof is correct and validating the previous state. So there is a verification process inside the generation of the proof, because generating the proof, you have to verify the previous proof. So this is why it is called recursive proof composition. So when we have to, if we want to construct a proof carrying data, we will need the technique of recursive proof composition. And I will explain how we can do this later. So after comparing these three kinds of verification processes, we know what we can buy from proof systems, and also know what we can buy from recursive proof composition techniques. So now let me go into a version of proof system, because it will be needed when we want to construct proof carrying data. So like proof system is to prove to others some computation is correct. And now I'm going to fix a representation of computation called the circuit representation. So like, for example, in our previous example, we have the whole state transition. This is the computation where we are aiming at, so in the right-hand side of the slide. And this whole computation, we can write it as a circuit. So a circuit like an electrical circuit. So like a circuit will consist of wires and gates. So we have input wires, and these input wires, we will connect these wires into gates, like the AND gate or OR gates and NOT gates. And there will be internal wires. And finally, after many wires and gates, there will be the output wires. So every computation can be represented in this way, which we call a circuit representation. And now we can consider, if we have a circuit, we can try to assign the values of the circuit wires. So let's distinguish two kinds of value assignment. The first is public values, and the second is additional values. So like for our example, the state 3 is public value, so that both the prover and the verifier have the values of the state 3. And now we don't need the verifier to have these additional values in blue. We only require the prover to have the additional values in blue. And so this is why we distinct between this kind of assignment. And we say that this, the public values, I will represent it as X, and the additional values will be represented as W, and they are colored as black and blue respectively. And if these values are like, if this computation is to be correct, we will say that this CXW equals 1, meaning that every gate is performed correctly, so that these wire values are consistent. Okay, so after describing, like abstracting this computation, we can now come to define what is a proof system. So, like we said, both the prover and the verifier have the circuit C, and they have the public input X. That is a partial assignment of the wires. And the prover additionally have this W. These are additional values that can make the whole circuit assignment be consistent. And so how does the prover prove to the verifier? We can follow the following syntax. So we have, so to describe a proof system, we will have three functions. The first function is a step function. It will take in a circuit of size within n, and then it will generate a proving key and verification key. And these keys are for proving and verification. So like this proving key and verification key actually encodes the circuit. And for the prover, it has both X and W. And it can use the proving key and these data to produce a small proof. And the verifier would only have X and the verification key. And if it also gets the proof, it can run the verification algorithm. And this is the algorithms we have. And what we would like to have, the property is that if the prover actually have X and W being satisfied by C, then if we follow these steps, we would want that the verification would pass. And also we want security. Security means that if if the prover is doing malicious things, so that the W is not actually some assignments that would make C correct, then it cannot convince the verifier. We can also state it in another way, that if some adversary can actually generate a proof that gets verified, then the X is actually, the adversary can actually generate the additional values W that attest to X. So this is like, if someone has W, it can generate a proof that gets verified. If someone can generate a proof that gets verified, then it can also generate a W that is correct. This is our requirements of non-interactive argument of knowledge. And we would like to have an additional efficiency property called succinctness. So for succinctness, it would require that the proof length is small and the verification time is small, because we want that the verifier delegates the loading to the prover. So we want that the proof that the verifier gets and the runtime of the verifier is very short. So it actually does not depend on the W. So because the W may be the history of the computation is very long, and for succinct arguments, we see that the proof length and verifier length will not depend on W. So for those familiar with snarks, we know that there are some parent-based snarks and hash-based snarks that satisfy these requirements. Okay. So this is a kind of proof system called snark. This is the option 2 in my example. And now let's see the option 3 of our example. The option 3 of our example, we can see that there are many verification units. Each unit is actually a state transition. So let's abstract the description of state transition. So initially, the state transition is from a state. After you have some transactions, you will compute the next state. And these three data have to satisfy a state transition rule. So I'll call this transition rule F, and I call X the state, and W the data for validating the state transition. So our option 3 proof pairing data will work as follows. There will be 3 algorithms, and the algorithms will follow similarly as the proof system. So first, we have a setup algorithm. So after we have fixed our state transition rule F, the setup algorithm can produce a proving key for proof and verification key for verify. And this proving key and verification key actually encodes the rule of F. And for proving, the prover will have, in addition to the state is going to claim. So the state is going to claim valid is X star. In addition to that, it will have to take in additional values. And now additional values is the previous state and the previous proof, X and proof. And also the data validating the state transition, W. So the prover, after having these things, it can produce a proof that attests to X star. So the verification algorithm simply takes the verification key, the state, and the proof, and it can verify whether this is valid. And for the semantic, we would require that if we process through a history of correct state transition from X0 to Xn, then and that we follow the process to produce using this proof algorithm to produce proofs for each X, then we actually have that the verifier will using Xn and proof n, it will have the verification to be correct. And for security, we would require that if some adversary can generate a proof that can verify, that can attest to Xn. So if this is verified to be true, then the adversary is actually capable of generating a history so that this history is valid. Okay, so this is what we want to construct, because this would this is the requirement we want, that if we have a proof that can get verified, then actually this state is coming from a true state transition process. Okay, so next, I'm going to give a high-level idea of how to construct this kind of proof pairing data from snarks and the technique of recursive proof composition. Oh, and before that, there's some remark. So in here, the proving time and the proof size is independent of the history length. So no matter how many previous steps we have processed, this does not depend on this history length, and the verification time is also with this property. So this is why in option 3 I said that we can the prover and verifier does not have to depend on the history length, and this is a fully scalable solution. Okay, so and actually the proof and verify can the time and the size can depend only roughly linearly on this state transition rule. So let's see how we can construct proof pairing data from snarks and recursive proof composition. So we have to consider a specific circuit. This circuit have its public input is the first parenthesis, vk and x star, and the additional values are the second parenthesis, wx and proof. So the circuit is designed so that it would accept if both of these two calculations are correct. So the first calculation is to use x star and w and x and compute whether x star actually comes from x using w. And the second computation is to run this verification algorithm with a verification key, vk. This vk comes from the public input. And the verification is against the public assignment, vk and x, and using this proof, pf. So it may seem a bit abstract what this circuit is actually doing. So like, because we don't know why we have this vk appearing twice in the verified algorithm, right? So let's see an example. So our example is to, because we use verify subscript n, so we have to start with a circuit D with size within n. And in this case, if we put this circuit D inside the setup and to generate a proving key and verification key, PKD and VKD, then now VKD can be put into this verify n as the first argument, right? So, so now if we pick a circuit D of size within n and we generate the corresponding proof key and verification key, and we can see what happens if we use this VKD as the public input of this circuit C. So in the fourth dot, we see that if we use VKD as VK, then this circuit accepts, implies not only that the state transition is correct, but also that the verification is correct. And the verification, we see that it is using the verification key VKD, so that the verification is actually being verified against, being verified over the circuit D. So it means that VKD and X is is some correct values for D, for the circuit D. So we now can see that when we construct this circuit C, the VK is an input, and in this, like at this stage, we does not actually know whether this which circuit this VK corresponds to, right? Because when we run setup, we can produce a verification key according to a circuit, and these two are related. So every verification key encodes a circuit, but in the input of C, the VK, we does not know which circuit it is corresponding to. But when we actually plug in a VKD, then we will know that it is corresponding to verification of D. So we know that the circuit accepts with VKD implies that VKD and X is acceptable by D. And what if we choose D equals C? If we can choose D equals C, this means that like C VKD X star accepts implies VKD X is acceptable by C, right? So we would have a like recursive exception. So VKD X star accepts implies that VKD together with the previous state is acceptable, and implies VKD with the previous and previous state is acceptable, and so on. So if we can choose D equals C, then we can have this recursive proof composition. But we know that we can only choose D with size within n. So if we want to use C, then the size of the C have to be within n. But we see that the description of the circuit is there are two parts. There are F and verify n, right? So let's analyze the size of the C. It would be F plus verify n, the size of the description of the two algorithms. And because we are using a snark, and this implies that the verification time would be much less than n. So if we pick large enough n, we would make C less than n. So that we pick such n, large enough n, and construct C. And the C will still have size within n. And then we can use C and put it in the setup phase to generate the proving key and verification key for C. And then plug this verification key for C inside this this argument in C. And then what we get is that when you verify using verification key of C against a state, it would mean that because if you verify correctly, it means that the circuit is satisfied, and which means that both the state transition is correct and that the verification of the previous state is also correct. And the verification is using the same verification key, BKC. So this logic continues to go on, so that we can have that every state is coming from a previous state correctly, and that the previous state runs the verification correctly. And so this is how we can construct PCD from snark and the recursive proof technique. Yeah, and so these are some references. So the first is about like the more theoretic concept of recursive composition, and the second and third one are some like implementations to make these constructions more efficiently so that they can be actually applied in practice. Yeah, and this is my talk today. Thank you.
Any questions for Chen? 你 Kara 我贾麦轩 Kevin。Mikara said good talk.
Thanks.
Sorry for a newbie question. Is this method also called an accumulator in some scenario, or there are completely different setup for recursive snark?
So accumulator is like we can construct recursive snarks with accumulators, but like it is a relaxed version. Like because here we construct PCD from snark, and we can also construct PCD from accumulators, and we can view accumulators as a relaxation of snarks. Not actually relaxation of snarks, because in snarks we have this a very important part is that we have this succinctness property, so that we can use this C to produce this BKC and to plug in the circuit C. But In other scenarios, we might don't have this succinctness property. And for those non-interactive arguments, they can have additional properties. And if they have these additional properties, they would be called accumulators. And these accumulators can make this can make the construction of PCD possible again. So they are like, that is another scenario we can construct PCD.
Got it. Thanks.